Okay, let's continue. And for question 4, I have recorded a separate video and of my conversation with a student on how to solve question 4. So if you haven't watched that video, and then please go ahead, and it is called Homework 2 question 4. Okay, so it is in our playlist. And the long story short, what we want to do is, well, in this case, for the induction, we want to start from n, and then if n is true, if for a certain value k it is true, and then we want to prove that for k plus 1 it is also true. So, well, you need to start from somewhere people can easily see, and then you build up and build up, and eventually you want to either decrease one side or increase the other side, and to build up to the target. So the target should be k plus 1 factorial is greater than k plus 1 cube. And then how do you do that? You want to start from here. This is the statement you want to prove. And then you can do cancels, and you can do increase on one side, increase one side, or decrease on the other side to make sure that it is still consistent. And one of the analogy I used to make is, say if we have two persons, and then we want to prove that person A is fatter than person B. So for example, I have the person A and the person B. And then I want to prove that the P1, person 1, is heavier than person 2. And then how do I prove that? And the easiest way is, well, if I can prove that for if person 1, and then I take out 1 pound from person 1, but person 1 is still heavier than person 2. And this means person 1 is guaranteed to be heavier. And say, let me get rid of this. Say person 1, for example, minus 1 pound is still greater than person 2. And this means, well, person 1 is heavier than person 2. So to prove person 1 is heavier than person 2, and what we can do is we can take 1 pound from person 1, and then we can yet prove it is still person 1 minus 1 pound is still greater than person 2. Or here is another thinking, or we can say person 1 is greater than person 2 even after person 2 has increased 1 pound. So we give a rock which is 1 pound, and then we ask person 2 to hold that. So person 2 plus a rock which is 1 pound heavy, and then it is still person 2 plus the rock is still lighter than person 1, and this means person 1 is heavier. So why do I talk about this? Well, those are some of the thinkings that when you are trying to cancel the parts on both sides to make the equation easier, and then you do have to think about how to cancel things. And when you build up and cancel things, and those are two strategies I use a lot. So anyhow, there is a video called Homework 2 question 4. Go ahead and watch this video. Okay? So I'm going to skip the question 4, and now it is question 5. So for the question 5, we have a recursive definition of the Tn. So, well, if you compare this version of the Tn versus the Tn we had in question 3, and there's a big difference. So usually what we do is, if we are able to do a polynomial Tn, so Tn is a polynomial of n, and then from this polynomial, we need to do two things. We need to prove the big O, and we need to prove the big omega, right? So for the big O, what is this? And then for big omega, what is this? So there are two things we want to prove from a polynomial Tn. And then after we are able to prove the big O and big omega, and then eventually we want to prove the big zeta. But now this Tn is different. This Tn is a recursive Tn, because to define Tn, there is a Tn divided by 2 here. So this makes it one step harder. So what we have to do is we start from recursive Tn. And then we want to, from the recursive Tn, we want to have a polynomial version of the Tn. And this process is called solving a recursion. Okay, so this is exactly what I asked you to do in question 5. You start from the recursive version of Tn, and you need to solve this recursive version of the Tn first, and then you get a polynomial version of Tn. And after you have the polynomial version of Tn, and then you have to prove the big O, big omega, and you need to prove the big O and big omega, and then big zeta. But for this question, if you prove it is big O, and that's enough. Okay, so let's start. Well, this is the polynomial version, this is the recursive version of the Tn. And then to solve this Tn, I have Tn divided by 2. So what is Tn divided by 2? So what we have is here. So we have, okay, so let me do this way. So what we have is, well, Tn equals Tn divided by 2 and plus a 4. So in this case, I don't know what is Tn divided by 2. So what I'm going to do is, I'm going to erase this n and then this n. I'm going to substitute this n and this n with n divided by 2. So this means for this part, this n, I want to plug in a n divided by 2 here, and this n, I want to plug in a n divided by 2 here. So this means t n divided by 2 equals t n divided by 2, n divided by 2 again, and then plus a 4. So if I want to massage this part a little bit, and this will give me t n divided by 4, and then plus a 4. Okay, so this is the value of t n divided by 2. So I'm going to substitute this Tn divided by 2 with Tn divided by 4 and then plus a 4 again. So now I have Tn divided by 4 and then plus 4 multiplied by 2. Okay, so now I have Tn divided by 4. And again, I don't know what is Tn divided by 4. So I'm going to start from this again. I'm going to substitute this n and this n both with Tn divided by 4. So I'm going to change this 2 to 4. I'm going to change this 2 to 4 again. So now I know Tn divided by 4 will be Tn divided by 8 and then plus a 4 again. So after I figure out what is Tn divided by 4, and then I'm going to substitute this Tn divided by 4 with Tn divided by 8 and then plus a 4. So this gives me Tn divided by 8 and plus 4 and then plus 4 multiplied by 2. Okay, so I can keep on doing this forever, but eventually what I want to observe is there should be a pattern. And the pattern is, well, Tn equals Tn divided by 2 powers k and then plus 4k. Okay, so the question is, where do we stop? So if this problem size is too small as 1, and then probably we want to stop, right? So it's just like the binary search. If the search space is 1, and then, well, we don't have to go divide this 1 into 2 again because there's only one value, and then we can't divide it again. So, well, let's just assume that when the size of the problem is too small and it's 1 already, and then we want to stop the divide and conquer, and then we just want to solve this problem. And then when this 1 equals the problem size, which is n divided by 2 powers k, and then we stop. And then what's the k value? K is log 2n. And then when this k is log 2n, we substitute this k here and this k here, and this will become the t1 and plus a 4 log 2n. So we assume that this t1 is going to be a constant time, and then we say, okay, when after we reach to the end of this divide and conquer, or we reach to the end of this recursion, and then this Tn will be a constant value and plus a 4 log 2n. So what we want to do is, well, we want to prove that there is an upper bound of this Tn. I'm going to try to use the constant as a 5, and then this Fn is the same. Is the same, so this is the log 2n here, and I'm going to do the log 2n here. So what I want to prove is, well, after a certain value, for example, n is 5, and then, well, this Tn, which is constant time plus a 4 log 2n, is going to be smaller than 5 log 2n. So I'm trying to find a upper bound of this Tn so that I can say, okay, so this Tn is O log n algorithm. Okay? So the next part, question 6. So for the question 6, well, we start from a recursive algorithm, and then we want to first try to do the recursive Tn to polynomial version of the Tn. Okay, and then how do we do that? Let's first find the recursive version of the Tn. So in the base case, we check the line 1 and then we return line 2. So this means in the base case, and then, well, the Tn will be a 2. And what if we are not at the base case yet? So we check this condition. This condition gives us a false. And then we are going to skip line 2, we go to line 3, and then we are going to try to find the line 4. And line 4 is recursive. And what it does is, if this array is big enough, let me get rid of this content here. So if this array is big enough, and then what I can do is, well, I'm going to keep one value odd, which is the first value. And then for the remaining n-1 values, I'm going to do a recursive call. So for this recursive call, it only handles, it only handles the max for this part. I'm holding the first value. I'm doing a recursive function call to grab the max of the remaining values. And then, so for this problem, this is the sub-problem I need to solve. And what's the problem size? The problem size is going to be n-1 here. Okay? So if the cost to solve the entire problem is Tn, and then to solve this sub-problem, the cost is going to be n-1. Okay? And then, well, after that, I'm going to do a comparison. So for the max on the remaining part, is it larger than the first value? If it's larger, I'm going to return the max of the n-1 values. Otherwise, I'm returning the first value. So if we count the recursive definition of the Tn, when we are not at the base case, this is the one line we want to execute, and this is one line. And then we check this condition, and based on this condition, we are going to either return this line or this line, right? So, well, this will give me a Tn equals Tn-1, and then plus a 3. So if we want to do that in the iterative way, so this is the Tn equals Tn-1 plus 3. This is the recursive definition of the Tn. And then if we want to keep on reducing the size of the subproblem we want to solve, and reduce again and reduce again, and what you will find that every time we reduce this problem size by one smaller, there will be a constant cost, which is 3. So we reduce and we reduce and reduce, and then where is the end? The end is when the problem size is a 1, and then so n minus k gives you a 1. So this problem is small enough, you can't reduce it again. So that's the base case, and then this will give you k equals n-1. And then when we substitute the k with n-1 here, this will give me t1 and plus 3 n-1. So this gives you a polynomial version of the Tn. So we started from here. So here we have a recursive version of the Tn. But then using the iterative method or substitution method, and then you will be able to get a polynomial version of the Tn. And once you have the polynomial version of the Tn, and again, you have to prove it is O, and it's big O and big omega. Once you have the big O and big omega, and then you can just claim that for the big zeta, it is n. Okay? So this is for question 6. And since this one, you got a linear version of the Tn, and then you can pretty much guess, well, it is a linear time algorithm. So the next one, if we have such a pseudocode, and then you want to prove that using the Message Theorem. Okay, so for this problem, the idea of solving, of finding the max is a little bit different. So if we have such an array, and what we do is we want to use a middle point to divide this array to two halves. So we are going to have the left half and the right half. So on the left half, which includes the mid, so the mid will be included to the left half. So for the left half, we want to do a recursive call so that we have the max of the left half. And then we want to do another recursive call to get the max of the right half. So, well, we are doing two maxes to solve, to find the max on the left half and the right half. And after that, we compare the value of the max of the left half and the max of the right half, and then we pick the higher one. So in this case, well, we can say, okay, so when we are at the base case, and then it's a constant value, and otherwise, I'm gonna try to visit one line, and then two line, and then this one, to solve this problem, the cost is gonna be t, n divided by 2, because it is the same algorithm, but we are finding the max for half of the values. And then this one, the cost of finding the max on the right half is going to be Tn divided by 2 again. Okay, so this one is Tn divided by 2. This one is Tn divided by 2, and then we do a comparison. So eventually, this is my version of the Tn. So, well, if the problem size is 1, and then it's a constant value, and otherwise it's a 2, Tn divided by 2, and then plus a 4. Okay, so now what do we do next? So for the Message Theorem, you need to answer 3 very quick questions after you have seen the recursive version of the Tn. What is the A? What is the B? And what is the Fn? So what is the A? A is a 2 here. And then what's B? B is a 2 here. And then, well, what's the Fn? Fn is 4, right? So this is constant time. Okay? So, well, the next question is, we want to say n powers log BA. Is that faster or slower than Fn? So in this case, n powers log BA is going to give you an n. So n is a linear growth, right? So n is a linear growth. And how about a constant value? Well, a constant value is like this. So which one grows faster? This is n, and then this one is constant. So which one grows faster? It should be n, right? So this means n powers log BA is faster. And then this will give you the case 1, and because it's a case 1 and it is theta n, and that's it. Okay? So for the Message Theorem, and it is indeed faster because you don't have to write really a lot to solve a recursion. And then you just need to answer the quick questions. What is A? What is B? What is the Fn? And then is Fn faster or low or slower than n powers log BA? And then by answering this question, and then you just you just want to find the right case, and then you can solve the recursion immediately. Okay, and then another thing I want to remind you is, well, for the Message Theorem, it can only solve the style like n. It can only solve the style like this one. So Tn equals A T n divided by B, and then plus Fn. Okay, so well, this has to be n divided by B here. So if it is n minus b instead of n divided by b, and then this problem cannot be solved using the Message Theorem. So it has to be a n divided by b here. Okay, so this is my solution to homework 2. And before I finish, I just want to remind you guys, and I'm holding office hours, and if you need my help, and feel free to come. Or if you want to have some face-to-face and one-on-one time, and shoot me email, and I can help you schedule that. And I'm here to help you, but you need to let me know you need my help. Okay, so have a good weekend. Have a good weekend, everyone. Bye bye.